Here's a third example where I'm going to be able to find the distance traveled by finding the area under the velocity curve. So I have a car traveling on a straight road. I have a piecewise linear function that gives me the velocity. And I want to know how far does the car travel between time 0 and time 24. So I'm going to check my units. Velocity is measured in meters per second, and time is measured in seconds, so that seconds and seconds match. So I won't have to do any conversion. And now we need to find the area under the velocity curve. So specifically, this is the area between the input axis, in this case the t-axis, and the v curve between time 0 and time 24. So I'm just going to shade that in. So you understand here. It's probably obvious in this picture, but we're going to have some more interesting velocity curves come up later. We want to make sure we really understand what do I mean by under the curve. So I've shaded that in. I recognize that as a trapezoid, sort of a geometry style trapezoid where the two parallel sides are horizontal. So I'm going to find the area under the velocity curve by finding the area of this blue trapezoid. So I'm going to find the average of the parallel sides. That side has length 24, specifically 24 seconds. And I'm going to average it with the length of that base. It's the difference between 4 and 16, which is 12. When I average, I add them up and divide by 2. I'm going to multiply by the distance across the other direction. So the distance between those two parallel sides is a vertical distance, and that is, I have a height of 0 here and a height of 20 here, so that distance is 20. That 20 is measured in meters per second, and my 24 and 12 are measured in seconds. So I'm going to multiply 24 plus 12 over 2 seconds times 20 meters per second. Any way you perform this calculation is fine. Notice you don't even actually have to simplify this calculation if you don't want to. So I'm going to cancel out a 2 there. I'm going to get 36 times 10, so 360 meters. So what are these? The next step here is the same as kind of what we had in the first semester. What if I want to find the slope of a curve, but I don't have enough information? My next step is to try to approximate it, because I'm going to have some times where my velocity curve, when I try to find the area underneath, it's not going to match up with some geometry shape that I already know. So we're going to think about a process we could use to make a good approximation, and then we're going to see if that leads us to a technique we can use to find an exact answer. So here we have one possibility, is I could take all of the, let me switch to here. So our technique here, we're going to try tiling in the area under this velocity curve with rectangles. We choose rectangles because rectangles are very easy to find the area of. All we need are the two dimensions, the width across the rectangle and the height of the rectangle. So watch what happens here. I have a velocity curve, 1/8 t squared plus 1. I'm going to make a t-chart here to figure out the velocities at each integer time value. I'm going to draw in the rectangles. So here's my t-chart. Sorry, it's running off a little bit off the screen. Let's try this. Okay, so you can see here that I have, when time is 0 and I use 0 in my velocity function, I get a velocity of 1. So that's where that, right, the blue curve, the velocity curve was already drawn in before we started. Now I'm interested to know at time 1, I can use this formula and I get that the velocity is 1 and 1/8. So that's that point right here. So I could, since areas of rectangles are so easy to find, I could try to fill in rectangles under the curve and see if that helps me get an estimate of what the area under the curve is. So notice the rectangle, I've just chosen here over these 4 seconds to use rectangles that are 1 second wide. I could make a different choice. And I'm going to have my rectangles meet up here at their top left corner. So for the rectangle that covers time 0 to 1, the left end of that interval is time 0. So I use the velocity, I use v of 0 as the height of my rectangle. So that's why I've drawn this horizontal line here. Now my rectangle is not a perfect match. You can see there's a little space left up there, but this is just something I'm trying. I'm gonna see if I can get an approximation of the area under this curve. So I can do the same thing. I'm gonna use at time 1, I'm gonna figure out v of 1, it's 1 1/8. And I'm gonna pretend my rectangle, well, I'm gonna make a rectangle that is that high, 1 1/8 high. And now I'm gonna make these 4 rectangles, and I'm going to use this sum of their areas to try to approximate the area under the curve. I know it's not going to be perfect. We can tell already it's going to be an underestimate because my rectangles don't touch those. They don't reach all the way up to the curve. Okay, so there's my rectangles with their top left corners touching. And now I'm going to do this area computation. So each one of these rectangles is 1 space wide. So 1 times 1 makes an area of 1. Here, a width of 1 times a height of 1 1/8 makes a total area of 1 1/8. Here, a width of 1 and a height of 1 1/2 makes a total area of 1 1/2. I'm going to add up all these areas. I'm going to get an approximation for the area under the curve, which is 5.75. I know just because of the way I've drawn the picture and I kind of walk through it so slowly that that's going to be an underestimate. I can see some blank spaces that under the curve that my rectangles don't touch. But that's okay. I'm just going out for approximation. When I have the left-hand corners of my the top left-hand corners of my rectangle touch the curve, we call this the left-hand rectangular approximation method, or for short, LRAM. So you can imagine I might do the same thing, but have the rectangles touch at their top right corner. So let's see what that looks like. You can see these rectangles happen to be a little bit too big because I'm letting them touch at their top right corner. So every single one of these rectangles happen to have a little bit of a little overestimate of the area it's meant to cover. Now when I add up the areas of these 4 rectangles, they still have a width of 1 each, but now I have a little bit bigger height values that I happen to be using for each one. I'm going to get a different approximation, but it's still a good approximation. Happens to be 7.75 is the approximation. We call this RRAM, or right-hand rectangular approximation method, since the right-hand edge of the interval tells you which Y value to use, which output value to use as the height of your rectangle. You might decide it's a better idea to make your rectangles touch at their midpoint. So here, if I want one rectangle to cover the distance between 0 and 1 second, instead of making it touch at v of 0 or v of 1, I can choose the value halfway between 0 and 1, which is 0.5. I could figure out the velocity at time 0.5 and use that. So here, I don't know, I've got a little overage here and a little underage here. I might decide that that's going to be a better choice for my rectangles because I'm going to have maybe a closer estimate. We'll talk more later about which method to choose, but just know that this is called midpoint rectangular approximation method, or MRAM. And as you might guess, that turns out to be an approximation that is between the RRAM and LRAM approximation that we got. So really what this is for is to introduce this idea of trying to tile in the area under a curve with rectangles, compute the areas of the rectangles because they're an easy computation to perform, and then using that as an estimate for the area under the curve. So something else to think about, if I wanted a better estimate, I could use more rectangles. Instead of saying, okay, from between times 0 and 4, I'm going to use 4 rectangles, I could make instead 8 rectangles, right? I could make one rectangle for 0 to 0.5 and another rectangle from 0.5 to 1 and then another rectangle from... In fact, I think that's what I have on exactly the next line. Just notice that that's one thing I know is going to improve my accuracy. If I could use more rectangles, I'm definitely going to have to do more computations, but even more important than picking which corner to touch at, using more rectangles is guaranteed to make my estimate a better estimate. So we're going to learn pretty soon how to find an exact answer. The same way that after we practiced finding slopes of secant lines first semester, we learned about derivatives and talked about rules for computing derivatives using algebra and calculus. So we introduced this because, number one, sometimes we will not have we won't have enough information to actually find an area under a curve, and we'll need to make an approximation. On the AP test, they'll expect you to be able to use LRAM, RRAM, MRAM. And because it's going to help us understand where the actual math that we're going to do to find exact areas, it'll help us understand where it comes from. So just a couple of important words. They used to show up on the AP test way more, but inscribed rectangles. Inscribed means it's completely inside the curve. So notice that none of those rectangles peeks out over the top of the curve. And here, circumscribed rectangles all overestimate their little chunk of the area. So they all have, every one of them has a little overage here, circumscribed. We'll talk more about when your rectangles are inscribed and circumscribed, but just to introduce that language. Now we're going to practice a little bit here using LRAM, RRAM, and MRAM to approximate areas under curves. On the AP test, they'll be very specific about how many rectangles you should use and whether you want them to touch at their left corner, right corner, or halfway across the interval. So LRAM, MRAM, or RRAM. We're going to practice all three here. Just notice it's not something you're going to have to choose on the AP test. They'll be very specific because they want to make sure they can grade your work against somebody else's. So they'll all have the same directions. So this is drawing the correct number of rectangles with the correct heights for each graph for the estimating the area under the curve from 0 to 6. Let's look at this one. I wrote here 6 rectangles. We're going to use LRAM. That means the top left corners are going to touch. And here's a hint. One of my rectangles will have a height of 0. So this isn't too bad if I'm going to have 6 rectangles that I want to cover the interval 0 to 6. I'm going to have each rectangle cover a horizontal distance of 1. So from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6. They're not going to mess with you on the AP test and make you have, use 5 rectangles to cover 6 seconds or anything strange like that. It'll be something pretty easy to calculate. So I'm going to look at my first rectangle. I want it to cover from the x values 0 to 1. And the left edge of the interval 0 to 1 is 0. So I'm going to use the output when the input is 0 to figure out the height of my rectangle. But check this out. For this rectangle, when the input is 0, the output is also 0, which means the height of my first rectangle is going to be 0. Which means later if I want to compute the area of that rectangle, it's going to be the area of a line segment, which is going to be an area of 0. My second rectangle is going to cover from 1 to 2. The left-hand edge of the 1 to 2 interval is 1. So I'm going to look at the output when the input is 1. It happens to be marked here already. You may not assume through this exercise that the dots are the tops of your rectangles. You're going to have to figure out the tops of your rectangles. So for the third interval, that's going to cover from 2 to 3. So I'm going to use the output when the input is 2 to figure out the height of my rectangle. Looks like about there. I'm drawing this rectangle. From 3 to 4, I'm going to use the height of the graph at time 3. At time 4, the interval from 4 to 5, I'm going to use the height at time 4 So that's going to be a rectangle that's an overestimate. So in the little PowerPoint I did, when I did LRAM, all the rectangles were too small. And when I did RRAM, all the rectangles were too big. It's not always a guarantee that the rectangles are going to be all too big or all too small. You're going to stick to this instruction and the rectangles come out like they come out. So from 5 to 6, I'm going to use the height of the rectangle at time 5. Oops. So now I have 1, 2, 3, 4, 5, 6 rectangles. This just says draw in. The rectangles didn't actually ask for an estimate. In the AP test, you'll be asked to actually perform the calculations for area, sum up the areas of those rectangles to make an approximation for the area. I'm going to leave these two to you. You're going to draw 3 rectangles using RRAM. You're going to draw 2 rectangles using MRAM.